Welcome to All in All. Prepare to have your mind stretched, because today we are embarking on a deep dive into one of the solar system's most enigmatic and, well, distant realms, the Kuiper Belt.
All right.
It's not just some vast, icy expanse out there. It's actually a dynamic, actively evolving region way beyond Neptune.
Uh-huh.
And it fundamentally challenges what we typically think of as, our cosmic neighborhood.
What's truly fascinating about the Kuiper Belt, I think, is that it's far more than just a collection of icy rocks. It functions as a dynamic fossil record.
A fossil record, okay.
Yeah, holding crucial, really pristine clues to how our entire solar system originally came to be. These objects are essentially time capsules.
Time capsules,
Yeah.
preserving materials from the very beginning.
Exactly. From the earliest moments of our sun's birth.
It's a powerful way to put it, a dynamic fossil record.
Yeah.
So how exactly do scientists go about reading that record? I mean, what are we hoping to uncover here?
Well, there's a lot we're still figuring out.
Our mission today is to thoroughly explore this incredible frontier. We're going to try and uncover its origins, understand its profound significance to the solar system.
Why it matters, basically.
Right. Examine its long-term evolution, delve into its past and ongoing impacts, and maybe even peek into its future practical relevance for humanity.
It's a big topic.
It really is. You're going to hear about everything from incredible cosmic ballets of planetary migration and violent ancient collisions to peculiar pancake-shaped objects, and even some really audacious ideas about future space exploitation.
Yeah, some pretty sci-fi stuff later on.
Definitely. The Kuiper Belt is one of those places that truly expands your mind, stretching far, far beyond what we typically imagine as our cosmic backyard.
And indeed, it's a region that continually reshapes our fundamental understanding of, well, a solar system's architecture and its history.
Okay, so to truly grasp the Kuiper Belt, we have to start at the very beginning. The birth of our solar system.
Yep.
The widely accepted scientific theory is that our planets, including Earth, formed in what's called a protoplanetary nebula, or solar nebula. That was about 4.6 billion years ago. Can you paint a picture for us? What did this chaotic, energetic, stellar nursery look like?
Certainly. Imagine a massive rotating disk of gas and dust. Huge, maybe hundreds of astronomical units wide, swirling around our newly formed sun.
Just a giant cloud.
Well, a disk, really.
Yeah.
And it wasn't uniform. It had varying densities, different temperatures, creating conditions for matter to start clumping together.
Okay.
A crucial aspect of this nebula was its incredibly high angular momentum, essentially, its rotational energy.
Right, the spin.
That spin prevented all that material from simply collapsing directly into the sun. Instead, it spread out into this vast, flat disk, like how a spinning pizza dough flattens out.
Aha, yeah, I can picture that.
That angular momentum is what ultimately distributed the material that would later form planets, asteroids, and, yes, the Kuiper Belt.
So it's not just a theoretical concept then. Our understanding of this process is constantly improving, especially now that we're discovering extrasolar systems and their own dust disks. We're actually seeing this happen elsewhere.
Precisely. Observing active protoplanetary disks around other young stars, like HD 141569A, for instance, allows us to test and refine our models of planet formation.
So we compare them.
Exactly. We can see gas and dust congregating, forming gaps, exhibiting structures that strongly suggest planets are forming right now. These distant observations provide crucial comparative insights.
Okay.
They help us confirm that the processes we hypothesize for our own solar system are in fact pretty common throughout the cosmos.
And when we talk about dating the solar system, it's not just guesswork, right? Or estimates from distant stars. We have something more concrete, like a cosmic birth certificate.
We do, actually. We rely heavily on leftover materials from that initial formation phase, particularly a type of meteorite called chondrites.
Chondrites. Okay.
These are sometimes referred to by scientists as pristine junk.
Pristine junk. It sounds contradictory.
It does, but it's because they haven't melted or undergone significant geological processing since they first condensed from the solar nebula.
Ah, I see. They're untouched.
Pretty much. So they preserve the exact chemical and isotopic signatures from that primordial moment. By analyzing these chondrites, we've pinned down the age of the solar system to an astonishingly precise 4.5672 billion years ago.
Wow.
With an uncertainty of just 0.6 million years.
That's incredible precision for something that old.
It really is. It's like finding a perfectly preserved, time-stamped fragment of the very first brick laid in our cosmic home.
That precision is truly remarkable. Okay, so now when we look at the Kuiper Belt's specific origin and its orbital evolution, how does that fit into this grand story? I understand there's a groundbreaking concept called the NICE model that really reshaped our understanding.
Ah, yes, the NICE model. Named after the city in France where it was developed. It offers a powerful framework for understanding the Kuiper Belt's origin and how the outer solar system got its current architecture.
Right.
It suggests something quite counterintuitive, actually. The protoplanetary disk, the one we just discussed. It was likely initially truncated or cut off at around 30 to 35 astronomical units, AU.
So, wait, that means the region where the Kuiper Belt is now was actually largely empty at the beginning?
That's what the model suggests, yes.
Yeah.
Empty at first.
So it wasn't always there in its current form. How did it get populated then? And what about our giant planets, Jupiter, Saturn, Uranus, and Neptune? Were they always in their current relatively stable orbits?
Not at all. The NICE model posits a dramatic and violent instability phase involving those very giant planets.
Violent instability. Sounds dramatic.
It was. Initially, they were likely much closer together in more compact, nearly circular orbits. But during this instability, their orbits became highly eccentric, chaotic, due to gravitational interactions.
So like cosmic billiard balls bumping into each other gravitationally.
You can sort of think of it like that, yeah. Strong gravitational tugs. For instance, Uranus and Neptune had a particularly strong interaction. Neptune got scattered outward by Uranus.
Outward?
Yeah, way out to an orbit around 27 AU with a pretty high eccentricity, about 0.3.
That's a big jump. Was it quick?
The scattering itself was likely fast, but the aftermath wasn't. Neptune's eccentricity then slowly damped, or smoothed out, over roughly 1 million years. And that happened due to something called dynamical friction.
Dynamical friction. Okay, what does that mean in this context? Is it like air resistance?
Not quite air resistance, but sort of analogous. Think of it like a subtle, persistent drag. As Neptune moved outward, it scattered countless smaller planetesimals, those icy bodies left over from formation.
Right, the building blocks.
Exactly. Each time it scattered one, that little object took a tiny bit of Neptune's orbital energy with it.
Ah, okay.
Over 1 million years, the cumulative effect of scattering billions of these smaller bodies acted as a kind of friction, gradually pulling Neptune's highly elliptical orbit into a more stable, circular one we see today. It's a bit like a massive ship slowing down as it plows through water, displacing it.
Okay, this is where it gets really interesting for me. The Kuiper Belt we see today wasn't always there. It was dynamically built, piece by piece, as our giant planets found their places. This planetary migration and instability sound like a chaotic cosmic ballet. What were the broader consequences of this massive planetary reshuffle?
You've hit on a key point. It was chaotic, but ultimately stabilizing for the long term. And it was absolutely crucial for shaping the entire outer solar system as we know it.
How so?
Well, this event explains the current architecture of the giant planets they're spacing, their nearly circular orbits. It also explains the existence of fascinating Trojan populations.
Trojans, like the asteroids near Jupiter.
Exactly. Groups of asteroids sharing an orbit with a larger planet, stable in its leading or trailing Lagrange points. Jupiter has famous ones, but Neptune has them too, likely captured during this migration.
Wow.
And perhaps most dramatically, it provides a strong explanation for the late heavy bombardment.
The period when the inner planets got pummeled.
Precisely. A period of intense asteroid and comet impacts that hit the inner terrestrial planets, including Earth and the Moon, roughly 4.1 to 3.8 billion years ago. The instability of the outer solar system likely flung many of these objects inward.
So if Neptune was migrating outward and scattering these planetesimals, how did those icy bodies eventually form the Kuiper Belt as we know it, instead of just being, kicked out of the solar system entirely?
That's the crux of it. And you're right, many were indeed ejected from the solar system, especially by Jupiter's immense gravity.
Okay.
But a significant number of them were gravitationally scattered into something called resonance sticking, near Neptune's mean motion resonances, or MMRs.
Resonance sticking. Sounds sticky.
It is, in a way. It's a subtle but powerful phenomenon that acts like a cosmic trap.
A trap? How does that work for an icy body?
Imagine a planetesimal getting nudged near one of Neptune's gravitational sweet spots. A mean motion resonance, like, say, a spot where it orbits twice for every 3 times Neptune orbits.
Okay, a ratio.
Exactly. Instead of being slung away entirely, it gets nudged onto a more stable, less elliptical path. More technically, when objects are scattered into the vicinity of an MMR, they can evolve to lower eccentricity orbits.
Less stretched out orbits.
Right. which effectively increases their perihelion distance, their closest approach to the sun, keeping them further from Neptune's strong pull, but still sort of locked in this resonant dance.
Yeah.
This sticking can persist for gig-years.
Billions of years.
Yeah, comparable to the age of the solar system.
Yeah.
It effectively prevents them from being easily ejected. This mechanism is key to explaining the structure we call the scattered disk within the Kuiper Belt today.
The scattered disk.
Okay. Though it's estimated only about 1% of the original Kuiper Belt population might have survived in it. These long-lived scattered disk objects are typically confined to perihelion distances between 30 and 40 AU, and their orbits can be quite tilted, up to about 40 degrees inclination.
That's fascinating, a kind of gravitational eddy current holding on to these objects. Is that the only way they get captured into these stable or semi-stable structures?
No, it's not the only way. We also have something called adiabatic resonance capture.
Adiabatic?
Yeah, it's actually a more efficient mechanism for capturing objects directly into resonances. It results in strong captures with small to moderate libration amplitudes.
Libration amplitude. Okay, that sounds technical again. What does that mean for how the object behaves? Is it wobbling?
You can think of libration as an oscillation, a gentle wobble around a perfectly resonant orbit. When we say small to moderate libration amplitude, it means the object is held much more tightly within the resonance, with less wobble in its orbital parameters.
More stable, then.
Exactly. Resonance sticking, on the other hand, the one we talked about first, leads to a weaker capture with larger libration amplitudes. The objects are held more loosely, allowing for more pronounced wobbling as they orbit. It's a subtle but important difference in how they interact with Neptune's gravity.
And are some resonances stickier or better at trapping these objects than others?
Absolutely. Numerical simulations basically running the nice model over and over again show that N1 sequences, meaning resonances where an object completes N orbits for every one orbit of Neptune, like the 21 resonance, the 31, the 41. Those are the most prominent sticky resonances for the scattering dynamic.
Okay.
They're followed by N2 sequences, like the 32 resonance where Pluto lives, or the 52.
And why those specific ones?
It's theoretically explained by the fact that these specific resonances have the largest stable libration zones. Think of them as offering the widest and most robust gravitational parking spots for these scattered objects.
Bigger parking spots, easier to get stuck in.
Essentially, yes.
Yeah.
And these zones decrease only slowly as you go to higher N values. So if we connect this to the bigger picture, this model effectively shows that the Kuiper Belt objects aren't just random debris.
Right?
They are remnants of the early solar system's planetary building blocks, forced into their current, often stable configurations by this precise yet chaotic cosmic ballet of gravitational forces involving our giant planets.
That's incredible. A true dynamic fossil record shaped by these immense gravitational forces over billions of years. So what does this all mean? The Kuiper Belt isn't just out there doing nothing. It's a cosmic archive shaping our solar system's past and even influencing its present. Let's delve deeper into why the Kuiper Belt matters so much.
Precisely. This pristine material from the Kuiper Belt is, well, invaluable. It helps scientists understand accretion, how things stick together, and evolutionary processes not just in our solar system, but also when we look at those dusty star disks forming around other young stars.
Yeah.
These objects are like untouched samples from our cosmic past.
Giving us direct evidence of conditions way back then.
Exactly. Direct evidence of the conditions present when planets were first forming. By studying their composition, their structure, we can infer things like the temperatures, pressures, the chemical makeup of the early solar nebula and its outer reaches. It provides crucial ground truth for our theoretical models.
And these interactions among KBOs themselves don't just shape their own dynamics, right? They also play a crucial role in creating the spectacular comets we sometimes see streaking across our night sky.
That's right. KBOs are a significant source of short-period comets.
Short period, meaning they come back relatively often.
Yeah, those with orbital periods of less than 200 years. Imagine a KBO in a somewhat unstable orbit gets a gravitational nudge maybe from Neptune, maybe even from another KBO sending it closer to the sun.
And it heats up.
Exactly. As it warms up, its ices sublime turn directly into gas, creating the characteristic coma and tails we associate with comets.
Okay, so the Kuiper Belt feeds us short-period comets. What about the long-period ones? Where do they come from?
That brings us to the Oort cloud. Beyond the Kuiper Belt, we hypothesize there's this vast spherical cloud of icy bodies surrounding the entire solar system.
The Oort cloud. I've heard of it, but it's still hypothetical.
Largely, yes. We can't observe it directly yet. But the long-period comets, the ones that can take thousands or even millions of years to orbit the sun, are thought to originate there. In fact, these long-period comets are considered the primary physical evidence for the Oort cloud's existence.
Their orbits point back to this distant region. How vast are we talking? Give us a sense of its incredible scale.
It's truly immense. It dwarfs the entire inner solar system. It's theorized to stretch from maybe 2,000 or 5,000 AU out to as far as 50,000 AU.
50,000 AU.
And some estimates even push its outer edge to 100,000 or even 200,000 AU from the sun.
That's mind-bogglingly far. What's that in light years?
Up to 3.16 light years. It's effectively 1/4 to 1/2 the distance to the nearest star, Proxima Centauri.
Wow. And it's not just one uniform cloud.
No, it's thought to be subdivided. There's a spherical outer Oort cloud and then a much denser inner donut-shaped region known as the Hills cloud.
The Hills cloud.
Yeah, named after Jack Hills, who proposed it. This Hills cloud is thought to contain tens to hundreds of times more cometary nuclei than the outer cloud. And it's crucial because it's believed to continually resupply the outer cloud.
Ah, like a reservoir.
Exactly. This explains why the Oort cloud still exists after billions of years, because comets are constantly being lost from the outer region, either ejected from the solar system or plunging inwards as active comets. The Hills cloud keeps feeding it.
So the Kuiper Belt and the Oort cloud are basically comet factories, just on different scales and making different types of comets. That's a huge impact on our inner solar system.
But does the Kuiper Belt itself, despite being so far out, have any measurable gravitational influence on the major planets like Saturn or Jupiter?
It does, remarkably, though it's incredibly subtle. This is one of the more impressive feats of modern astronomy, actually.
How can they tell?
Scientists have managed to weigh the Kuiper Belt by observing its tiny, almost imperceptible gravitational perturbation on Saturn's orbit.
On Saturn, even though Neptune's closer. Well, Saturn's orbit is known incredibly precisely, and these subtle, long-term tugs add up. Through incredibly precise astrometry measuring positions and movements and sophisticated orbital models, they've deduced the Kuiper Belt must have a certain total mass to account for those minute deviations.
So what's the estimate? How much does it weigh?
The current estimate for the Kuiper Belt's total mass is about 3.6 by 123 kilograms.
Which is how much compared to Earth?
Roughly 6% of Earth's mass.
Only 6%. That doesn't sound like much.
It might sound small compared to a planet, but it's still a significant amount of mass spread over a vast region, and it demonstrates a measurable, albeit subtle, influence on the inner solar system's long-term dynamics, like a gentle gravitational anchor way out there.
That's incredible that we can weigh something so distant just by watching Saturn wobble slightly. And what about moons? Are some of the giant planets moons objects we've actually visited with spacecraft connected to the Kuiper Belt? Did they come from there?
Yes, absolutely. Some moons of the giant planets are strongly believed to be captured KBOs. They offer direct, tangible evidence of the belt's dynamic past.
Like which ones?
A prime example is Neptune's largest moon, Triton.
Triton, right. Voyager 2 flew past it.
It did back in 1989, and it revealed this bizarre, geologically active world, ice volcanoes, nitrogen geysers, just amazing stuff.
But how do we know it was captured?
The biggest clue is its orbit. It's retrograde.
Meaning it orbits backward.
Exactly. It orbits Neptune in the direction opposite to Neptune's rotation and opposite to all of its other major moons. That kind of orbit is extremely difficult, almost impossible to form alongside the planet. Capture is the most likely explanation.
Okay, that makes sense. Any others?
Another clear example is Saturn's small outer moon, Phoebe. Cassini visited it in 2004.
Phoebe, right, the dark, irregular one.
That's the one. Like Triton, Phoebe has a retrograde orbit. It's dark, irregularly shaped, and its composition appears similar to some KBOs. All strong indicators that it was once a free-floating object, likely from the primordial Kuiper Belt, that got snared by Saturn's gravity during that early chaotic period.
This all brings us inevitably to one of the most famous, or maybe infamous, stories related to the Kuiper Belt, the whole Pluto debate. Tell us how Pluto's status as a planet came into question, and what that whole saga taught us about the solar system.
Ah yes, Pluto. The story begins way back in 1930, with Clyde Tombaugh's discovery.
He was looking for Planet X.
Right, exactly. He was diligently searching for a hypothetical ninth planet thought to be perturbing Neptune's orbit. He used this painstaking technique called blink comparison.
Flicking between photos to spot movement.
Right, rapidly switching between photographic plates taken on different nights to spot tiny moving specks against the fixed stars. And he finally found Pluto, roughly where Percival Lowell had predicted.
And it was instantly called a planet.
Pretty much. Initially, it was classified as the ninth planet. It made sense at the time. It looked bright, seemed relatively large, though we now know its size was overestimated back then. Its odd orbit, elliptical and tilted, was noted, but it didn't immediately challenge its planetary status.
But then things started changing. Discoveries were made.
Things changed dramatically in the early 2000s. Astronomers started finding more and more large objects out in the Kuiper Belt. And then, in 2005, came the discovery of Eris by Mike Brown and his team.
Eris. And that one was initially thought to be bigger than Pluto, wasn't it?
It was. That's when the conversation really heated up. The scientific community realized, okay, we have a problem. If Pluto is a planet, then is Eris a planet? What about Sedna, Quaoar, Makemake, Haumea, all these other big KBOs being found? Where do we draw the line?
So that forced a decision.
It forced a definition. This led to that pivotal meeting of the International Astronomical Union, the IAU, in 2006. They convened specifically to redefine what it means to be a planet.
And they came up with those 3 criteria.
Right. A celestial body must orbit the sun, be massive enough for its own gravity to pull it into a nearly round-shaped hydrostatic equilibrium, and the crucial one, it must have cleared its neighborhood of other objects.
And Pluto failed that last one.
It did, along with the Ceres in the asteroid belt. Pluto's orbit is full of other KBOs, many in similar resonant orbits. It hasn't gravitationally dominated its region in the same way the 8 planets have, so it was reclassified as a dwarf planet.
Which caused quite a stir. I remember the headlines, even hate mail from 3rd graders for some astronomers involved. And I know there's still an ongoing debate among planetary scientists, isn't there? Not everyone agrees with the IAU definition.
There certainly is. Many prominent scientists, like Alan Stern, who's the principal investigator for the New Horizons mission that flew past Pluto, they prefer what they call a geophysical definition for a planet. Under this view, any celestial body that's massive enough to be round due to its own gravity would be considered a planet, regardless of what's in its orbit. Stern actually coined the term dwarf planet way back in 1991, intending it as a subclass of planets, not a demotion.
Interesting. So the debate continues.
It does. But this whole episode, while controversial and passionately debated, ultimately did something important. It highlighted the incredibly dynamic and diverse nature of the Kuiper Belt itself.
How so?
It forced us to recognize Pluto not just as a lone oddball planet, but as the king of the Kuiper Belt, the largest, most complex, most fascinating world within this distinct region of the solar system.
That's a good way to look at it. It raises an important question, though. If we hadn't discovered the Kuiper Belt and all those other objects, would Pluto still be called a planet today?
It is very likely it would be, yes.
And what does that tell us about how we define things, how we understand our cosmic neighborhood?
It tells us that science is a process. Definitions are not static. They adapt and evolve as our knowledge grows. Finding the Kuiper Belt fundamentally changed our understanding of the solar system's layout, and our definitions had to catch up.
That's a powerful point, and it truly puts the Kuiper Belt into perspective, not just a distant region, but a fundamental shaper of our understanding. So what does this all mean? The Kuiper Belt isn't just out there, it's this living cosmic archive shaping our past, influencing our present.
And it continues to evolve even now. The Kuiper Belt is far from static. It's constantly being sculpted by its own objects and even by echoes of forces from the early solar system.
Absolutely. It's not just a static ring of ice. It's constantly being sculpted. Let's delve into its long-term changes, maybe starting again with that realm of instability we mentioned, the scattered disk.
Right, the scattered disk. It's a truly dynamic and, well, unstable environment. Objects there have orbits that are constantly at risk of disruption because of Neptune's ongoing gravitational perturbations.
They're not locked in stable resonances like Pluto.
Not typically, no. They're on these more eccentric, often inclined orbits. And because of that instability, they can be sent outwards, potentially flung all the way out into the distant Oort cloud, or they can be sent inwards, transforming into centaurs.
Centaurs. Those are the icy bodies that cross the orbits of the giant planets, right? Like Chiron.
Exactly. They bridge the gap between the Kuiper Belt and the inner solar system. And eventually, many centaurs are expected to become Jupiter family comets, those short period comets we talked about earlier.
So the scattered disk is like a cosmic conveyor belt, feeding objects both outwards and inwards.
That's a good way to put it, yeah. A transitional zone.
No.
And unlike the more classical KBOs, which tend to have lower inclinations, these scattered disk objects can have orbits tilted way up, sometimes 40 degrees or more, from the ecliptic plane where most planets orbit. It reinforces that sense of dynamic chaos.
Which is why some astronomers prefer scattering disks.
Precisely. It emphasizes the ongoing, active, dynamic process rather than just a static state of being scattered.
Okay. And what about those really weird ones, like Sedna? You mentioned detached objects.
Yes, Sedna is fascinating and frankly baffling. Its perihelion, its closest approach to the sun, is way out at 76 AU.
76? That's incredibly far. Neptune's at 30 AU.
Exactly. And its average orbital distance, its semi-major axis, is over 500 AU. Sedna is far too distant from Neptune to be significantly influenced by its gravity today. It seems detached.
Are there others like it?
Yes. Another example is an object called 2000 CR105. These objects hint at maybe an extended scattered disk, or perhaps they're part of an inner Oort cloud population that we're just starting to glimpse.
But what could put them on such strange orbits, so far from Neptune's influence?
That's the million-dollar question. Their unusually elongated and distant orbits suggest they require some kind of external agent, some other gravitational influence.
Like what?
Well, theories include maybe the sun forming in a much denser star cluster early on, where it close passes by other stars, could have perturbed these objects. Or perhaps interactions with a rogue planet that got ejected from our solar system. Or, more controversially, maybe there's an undiscovered planet, a Planet 9, lurking far out there, gravitationally shaping these orbits.
Planet 9. Still hypothetical, but these objects are clues.
They are tantalizing clues, yes.
Yeah.
These detached objects are truly the outliers, probing the very edge of our sun's gravitational influence and hinting at dynamic events we don't fully understand yet.
That implies massive forces shaping our solar system, maybe even still today, or at least in its ancient past. Speaking of the past, you mentioned earlier that the Kuiper Belt has a significant mass deficit. What exactly does that mean, and where did all that mass go?
Right, the mass deficit is one of the big puzzles. Our models of planet formation suggest that the primordial Kuiper Belt, the PKB, should have been vastly more massive than what we see today.
Oh, much more massive.
Probably 2 to 3 orders of magnitude larger, so 100 to 1,000 times more massive, maybe containing 10 to 30 Earth masses worth of solid material originally.
Wow, that's huge. Why did it need to be so massive?
Because you need enough stuff colliding frequently enough for objects to grow to the sizes we see, like Pluto or Eris C, within a reasonable time frame, say 10 to 100 million years. Accretion is inefficient out there where orbits are slow.
Okay, so we need a lot more mass to build the KBOs we see. But what do we see now? How much mass is actually there?
The current Kuiper Belt is estimated to have a total mass of only about 0.03% of what should have been there. That's a huge discrepancy.
It is a massive difference. And this isn't just a number. It challenges our fundamental assumptions about how much raw material was available and how efficiently planets formed in the early outer solar system. It forces us to rethink the very blueprint of our cosmic neighborhood.
So where did all that missing mass go? Was it all just flung out by Neptune's migration? That's part of the story, but probably not all of it. The prevailing theory combines Neptune's migration with something called collisional grinding.
Collisional grinding sounds destructive.
Yes, very. During that early chaotic phase, when the primordial Kuiper Belt was much more massive and its objects had larger eccentricities and inclinations, they were zipping around more wildly, they would have experienced incredibly intense and frequent collisions.
Smashing into each other constantly.
Pretty much. These impacts would have rapidly comminuted or pulverized most of the original mass into fine dust.
And what happened to the dust?
It was then efficiently removed from the system. Solar radiation pressure, the push from sunlight, and another effect called Poynting-Robertson drag, which sort of spirals tiny particles inwards towards the sun, cleared out the dust relatively quickly.
So Neptune stirred things up, causing collisions that smashed most of the mass into dust, and then the sun cleaned the dust away.
That's the basic idea. The PKB dynamically lost a huge fraction, maybe a factor of 1,000, in population as Neptune migrated through it, driving objects onto Neptune-crossing orbits where they could be scattered or ground down.
How many actually hit the planets?
Our models suggest only about 1% of this destabilized population eventually hit Jupiter, with even smaller fractions hitting the other giant planets or their icy moons. The vast majority was either ejected from the solar system entirely or ground down into that dust.
And these collisions would have been most intense early on, right? When the Kuiper Belt was at its most massive and dynamic.
Absolutely. The impact rate, say, on Jupiter from PKB bodies dropped by 4 orders of magnitude. That's a factor of 10,000 over the 4.5 billion years of solar system history.
Wow.
So the highest impact flux, the most significant collisional grinding and mass loss happened very early on during that initial violent instability phase.
And can we see evidence of this bombardment?
We think so. Objects like Phoebe, the captured Saturnian moon we discussed, likely originated in the PKB and was captured during this instability. Its heavily cratered surface acts like a historical record, providing crucial constraints on what that incredibly active, collision-filled primordial population must have looked like.
It's incredible to think about the sheer violence that shaped this seemingly quiet, frozen region we see today.
It truly is. What's fascinating here is how these subtle changes over billions of years, like the surface colors we see, offer a window into the long-term evolution of these incredibly distant worlds.
Right, the colors. Beyond their dynamics, what can we say about the physical properties of KBOs? What are they actually made of? And why do some look red and others blue-gray?
Compositionally, the dominant material is water ice, often in an amorphous, non-crystalline state because it's just so incredibly cold out there, below about negative 220 degrees Celsius.
Amorphous ice, like glass.
Sort of, yeah, lacking a regular crystal structure. But it's not just water. They also contain various other ices, things like carbon monoxide, methane, methanol, ammonia. These are known as volatiles, meaning they turn into gas relatively easily if warmed up.
Okay, lots of ices. Anything else?
Yes. Besides the ices, we find more refractory or heat-resistant materials, things like amorphous carbon, silicates, which are common rocky minerals, other stony materials, traces of sodium, carbonates, simple hydrocarbons, and even clays have been detected or inferred. They're complex, frozen worlds, definitely not just simple, dirty snowballs.
And the colors. Some are strikingly red, while others are more blue-gray. What causes that difference?
That's a really interesting area of research. The red color, which is quite common out there, is thought to arise from space weathering. Cosmic rays, high-energy particles from space, and solar ultraviolet rays constantly bombard the surfaces. When this radiation strikes carbon-containing compounds on the icy surface, like methane or methanol, it triggers chemical reactions over vast timescales, billions of years. This forms complex organic compounds, sometimes called tholins, which tend to be reddish-brown. This builds up in a radiation mantle, or crust, on the surface.
So they get a sort of cosmic sunburn that turns them red over time.
That's a decent analogy, yeah. The blue-gray color, conversely, might result from more recent impacts. Smaller collisions could excavate or uncover fresh, new layers of pristine, unradiated ice from beneath that ancient, reddish crust.
So blue means younger surface, red means older.
It's likely more complex than that, depending on the original composition too, but that's the general idea. It's a dynamic process of cosmic weathering, and impacts constantly changing the appearance of these distant bodies.
Do the larger KBOs like Pluto and Eris show different compositions compared to the smaller ones?
They often do, yes, and it gives us fascinating insights. Larger KBOs like Eris, Pluto, Cetus, and Quasar show clear signatures of methane ice in their spectra, the unique patterns of light they reflect.
Why them specifically?
It's largely because their higher gravity allows them to hold on to such volatile ices over billions of years. Smaller objects might lose lighter gases like methane to space more easily over time.
Makes sense.
Some of these larger ones also show signs of methanol or even ammonia. Ammonia ice is particularly interesting because it hints at very cold, primitive conditions, maybe reflecting the chemistry of the outer solar nebula when these objects first formed. It's like finding frozen snapshots of the early solar system's chemical inventory.
It's truly mind-boggling to consider we can discern such fine details about their chemistry and history from billions of miles away. Just incredible technology. And speaking of exploring, it's one thing to observe this region, but imagine actually going there more often, maybe even building things or living out there someday. That thought is mind-boggling in a different way.
Indeed. And we have to remember, our empirical knowledge, our direct observations of the Kuiper Belt are still in their early stages. You could compare it to our understanding of the asteroid belt back in, say, 1960.
Before we had sent probes there.
It's exactly. Before extensive telescopic surveys and eventually spacecraft missions like Dawn or near Shoemaker revolutionized our view of asteroids. We've come a long way with the Kuiper Belt, but there's so much more to learn.
But we have sent missions out there, right? We're not just relying on telescopes anymore.
We have. Pioneer 10 was technically the first spacecraft to enter the Kuiper Belt region way back in 1983, when it crossed beyond Neptune's orbit.
Did it see anything?
Not really. Its instruments weren't designed to detect individual small, dim KBOs. The true dawn of Kuiper Belt exploration came much later, with NASA's New Horizons mission.
New Horizons, launched in 2006, flew past Pluto in 2015.
That's the one. It was the first spacecraft to actually visit an object in the Kuiper Belt, performing that spectacular flyby of Pluto and its moons.
And those images were absolutely stunning, weren't they? They completely changed our perception of Pluto from just a fuzzy dot to a complex, active world.
They were utterly revolutionary. New Horizons provided images and data thousands of times more detailed than anything before. It revealed Pluto as this dynamic world with incredibly rich, varied landscapes.
Like what? What did we see?
Vast plains of nitrogen ice, like Sputnik Planitia. Towering mountains made of water ice acting like bedrock. Evidence of cryovolcanism, ice-spewing volcanoes. Deep, jagged canyons. It fundamentally transformed our view, showing Pluto to be far more geologically active than almost anyone had predicted.
Amazing. And it has moons, too.
5 moons, yes. With Charon being almost a binary companion, locked in this fascinating orbital dance with Pluto.
And New Horizons didn't stop at Pluto, did it? It kept going, visited an even more distant Kuiper Belt object, Arrokoth. What did that tell us?
That's right. On New Year's Day 2019, New Horizons flew past Arrokoth, making it the most distant object ever explored up close by a spacecraft.
And it looked really weird, didn't it? Like 2 pancakes stuck together.
Huh? Yeah, the pancakes joined at the hip, or snowman structure. It's what we call a contact binary. 2 distinct lobes that gently came together in the early solar system and just stuck.
What does that shape tell us?
That unique shape, combined with its relatively smooth, pristine, reddish surface, provides crucial clues about one of the most fundamental questions in astronomy. How does gas and dust initially clump together and grow into larger bodies? Those very first steps of planet formation. Arrokoth looks like a primordial planetary building block, frozen in time, showing us gentle accretion rather than violent collision.
Incredible. Okay, so what about future observations? Are we going to find thousands more of these amazing objects soon, maybe revolutionizing our understanding even further?
Absolutely. The big game changer on the horizon is the Vera C. Rubin Observatory, formerly known as LSST.
The Large Synoptic Survey Telescope. When does that start?
It's slated to begin its main survey operations very soon, possibly next year. Over 10 years, it will repeatedly photograph the entire visible southern hemisphere sky with unprecedented depth and speed.
And it's expected to find lots of KBOs.
Lots. Researchers anticipate it will find approximately 40,000 more KBOs, maybe even more. This will dramatically increase our sample size from the hundreds we know well now to tens of thousands.
What will that allow us to do?
It will enable powerful statistical analyses of KBO orbits, compositions, populations, and distributions. This will deepen our insights into early solar system evolution, test the predictions of the NICE model in much greater detail, and maybe, just maybe, uncover definitive evidence or constraints on that hypothetical Planet 9 through its gravitational influence on these distant objects.
That's incredible potential. And New Horizons itself, is it still going? What's next for that pioneering spacecraft? Is it going to visit anything else?
It is still going strong, yes. Its mission has been extended as of fiscal year 2025, primarily to gather unique heliophysics data.
Studying the sun's influence way out there.
Exactly. Studying the conditions in the outer heliosphere, that vast bubble of solar wind surrounding our sun from its incredibly distant vantage point. It's operating in a low-activity mode to preserve fuel.
So no more KBO flybys planned?
There isn't a known, compelling flyby candidate reachable right now. However, this extended mission keeps the possibility alive. If Rubin or other surveys identify a suitable KBO along its future path relatively soon, a flyby could potentially still happen. They're conserving fuels just in case. It's a testament to incredible engineering and mission planning.
The sheer scale of these missions, the distances involved, it's just immense. What are the biggest hurdles, the biggest challenges to exploring a region like the Kuiper Belt more often, especially if we dream about sending more probes or even eventually humans?
Oh, the challenges are indeed immense, almost overwhelming, really. First, there's just the sheer distance. The Kuiper Belt spans from about 30 AU out to 55 AU or beyond.
Which makes communication incredibly hard.
Incredibly hard. Radio signals weaken significantly with distance. It follows the inverse square law. So a signal gets dramatically fainter the further it has to travel.
Like a flashlight beam spreading out.
Exactly. Transmitting data efficiently back to Earth from billions of miles away requires incredibly sensitive receivers and huge antennas on Earth, like those of the Deep Space Network. And the spacecraft needs powerful transmitters and high-gain antennas pointed accurately back home.
And the travel time itself must be enormous. We're talking about decades just to get there, aren't we?
We are. Even with our fastest current rockets, using the most energy-efficient trajectories, what we call Holman transfers, well, reaching the Kuiper Belt, say 40 AU, can take up to 45 years.
45 years, that's a career, a lifetime almost.
It is. Even with more advanced low-thrust propulsion systems, like ion engines that provide continuous gentle acceleration over long periods, they still require incredibly high delta-v, or change of velocity, and while they might shorten the trip somewhat, we're still talking decades-long travel times.
Which requires incredible patience, long-term planning.
Multi-generational commitment from scientists and engineers, and the political will to fund missions that might not yield their primary results for potentially 50 years or more.
So we fundamentally need better technology just to get there faster and communicate more effectively. It sounds like a problem of power and propulsion, mainly.
Precisely. Future, more ambitious missions will require truly advanced propulsion systems. We're talking about things like nuclear electric propulsion.
Using a reactor to power ion engines.
Exactly. Or even more exotic concepts like fusion propulsion, though that's still very much in the realm of basic research. These systems could potentially cut travel times significantly, maybe down to 10, 20 years instead of 40, 50.
That would be a game changer. What about communication?
Beyond just bigger antennas, the future is likely in optical communication, using lasers instead of radio waves to transmit data.
Like fiber optics, but through space.
That's the idea. It offers much higher bandwidths, allowing more data to be sent back much faster. And of course, the spacecraft themselves need to be incredibly robust, reliable, with extensive redundancy and fault tolerance built in. They have to survive for decades in the extreme cold, vacuum, and radiation-filled environment of deep space, far, far from any possibility of repair.
This all sounds like a prelude to something even more ambitious than just observation and flybys. Tell us about this vision of Kuiper Belt exploitation, or KUBE. That sounds like something right out of a science fiction novel.
KUBE, yes. It stands for Kuiper Belt exploitation, and it's an incredibly ambitious concept study being looked at by DLR, the German Aerospace Center.
And their goal?
Their stated goal is, and I quote, to erase fiction from presumably science fiction ideas. They're seriously investigating truly innovative concepts for future space technology and resource utilization, pushing the boundaries of what we think is possible.
So what does this semi-self-replication mission layout they propose actually entail? It really does sound like something from a futuristic movie.
It does, but they're trying to ground it in engineering principles. The proposed layout involves sending an initial autonomous factory, a sophisticated robotic explorer, and manufacturer to a suitable KBO.
A factory in the Kuiper Belt.
Yes. Once there, this factory would use the belt's abundant resources, primarily water ice, but also other volatiles like methane or ammonia, and maybe some rocky materials to create mining and explorer rovers.
It builds robots using local materials.
That's the concept. These rovers would then go out, gather more resources, bring them back to the factory, allowing the factory to produce even more rovers, and, crucially, more factories.
Wow, so it grows itself.
Effectively, yes. Creating a self-sustaining, potentially exponentially growing network for resource extraction and manufacturing directly in the Kuiper Belt. The idea is to scale up operations significantly without needing constant expensive resupply missions from Earth.
That's a truly bold vision. How would they actually get the resources out of these icy worlds? It's incredibly cold, the surfaces might be rugged.
They envision several methods tailored to the conditions.
Mm-hmm.
One key idea is cold trap ice mining.
How does that work?
You use a concentrated heat source, maybe focused sunlight or nuclear heat, to sublimate the ice, turning it directly into gas without melting at first. This gas is then directed towards extremely cold plates or surfaces. When the gas hits the cold plate, it recondenses, freezes back into solid, pure ice. You've effectively trapped the volatiles.
And then you collect it.
Exactly. The captured water, methane, or ammonia ice can then be transported, perhaps liquefied for storage, or simply scraped off the cold plates. For deeper materials or loose surface regolith, they'd likely use more conventional methods like core drilling, which we use on Earth and Mars, and simple scoops or excavators.
And the ultimate goal isn't just gathering materials, but manufacturing things in situ, right there in the Kuiper Belt. What kinds of things could they produce?
Exactly. The ability to produce spacecraft components, and especially propellants, directly in the Kuiper Belt is seen as a potential game changer for future space exploration.
Rocket fuel made out there.
Yes. Things like hydrogen and oxygen from water ice, or maybe hydrogen peroxide, methanol, methane, hydrazine, depending on the available resources and the propulsion systems being used. This would drastically reduce the amount of mass we need to launch from Earth's deep gravity well, because fuel makes up the vast majority of a rocket's launch mass.
How would they make components?
Three-dimensional printing, or additive manufacturing, is being seriously investigated as a versatile method for autonomous spacecraft reproduction and component fabrication. Imagine printing spare parts, or even entire small probes, on demand.
Are there challenges of 3D printing in space?
Oh, definitely. Making it work reliably in zero or microgravity, especially with materials processed directly from raw KBO resources, is still a significant engineering obstacle that needs a lot more research and development.
But if they could achieve this, the applications are enormous. Fueling missions further out, building infrastructure, maybe even supporting human missions into interstellar space someday.
The potential applications are vast and frankly audacious. This kind of capability could enable transporting huge amounts of resources, water, fuel, building materials back to planetary outposts, perhaps on Mars or the Moon, or to space stations in Earth orbit, making our presence in the inner solar system far more sustainable.
And beyond the solar system.
More ambitiously, yes. It could make interstellar crewed missions far more feasible. Imagine using a large KBO as a massive, tethered counterweight for artificial gravity generation during long voyages to other star systems. You could spin the spacecraft around the KBO, creating a comfortable Earth-like gravity environment for the crew inside.
Wow.
And perhaps the most audacious concept is building true starships inside the protected, resource-rich environment of large KBOs. Leveraging the abundant water ice for propellant and radiation shielding, using the metals and silicates for construction, building our interstellar vehicles right where the resources are, poised for the journey outwards.
This raises a huge question, though, maybe the most important one. If we truly manage to harness the resources of the Kuiper Belt, or even asteroids closer in, what are the ethical and economic implications back here on Earth? How do we ensure this new frontier benefits all of humanity, not just a select few? I know I've heard astrophysicists like Neil deGrasse Tyson speculate about asteroid mining creating the first trillionaire.
That's a parallel that's often drawn, absolutely. And it brings up a crucial, complex debate. Supporters of space mining, including some prominent voices, envision it as a catalyst for an unprecedented new space economy.
More than just resources.
Yes, potentially enabling large-scale space tourism, settlement, new industries we haven't even conceived of yet. Some argue that accessing vast extraterrestrial resources, metals, water, volatiles, could even reduce the prevalence of unethical labor practices on Earth, like child labor sometimes used in mining critical minerals in certain regions, by providing an alternative, perhaps automated source. It's a vision of a new era of abundance and opportunity.
That sounds incredibly optimistic, almost utopian. But there's a significant counterargument to that economic coin, isn't there? The potential for massive disruption.
There is a very real and potentially very severe counterargument. Many economists and policy experts warn that large-scale asteroid or Kuiper Belt mining could rapidly destabilize or even destroy the global economy for raw materials.
How so?
The current global market for raw materials is valued at something like US $660 billion annually. Now imagine introducing potentially quintillions of dollars worth of materials, platinum, gold, rare earths, water from space. If that material floods the market, it could cause a rapid and unprecedented devaluation of those same resources here on Earth. This isn't just theoretical, it's a concern actively being modeled.
And this wouldn't affect everyone equally, would it? Developing nations that rely heavily on mineral exports could be hit hardest.
Precisely. Researchers, for example, at Tel Aviv University have run simulations exploring these scenarios. They predict a significant potential for a global struggle for resources and power. One simulation showed that even a single, relatively modest shipment of space minerals could theoretically devalue the price of gold on Earth by 50%.
50%? That's huge.
It is. Now, consider the implications for developing countries whose economies are heavily reliant on exporting specific minerals. Think cobalt from the DRC or platinum from South Africa. They often lack the immense resources and technological infrastructure needed to build their own space mining operations.
So they could be left behind, or worse.
They could see the value of their primary exports collapse. Imagine the economic disruption if a single large corporation effectively cornered the market for a natural resource vital to a nation's entire economy. It's a complex ethical and economic minefield we would face as we expand into this new frontier. How do we balance the potential benefits of abundant new resources with the very real risk of devastating existing economies and exacerbating global inequality? It's a conversation we need to be having now, long before it becomes a reality.
And that, listeners, brings us towards the end of our deep dive into the Kuiper Belt today. What a journey. We've traveled from its violent, unstable birth, shaped by that tumultuous migration of the giant planets,
Billions of years ago.
to its profound significance as a cosmic fossil record, preserving the pristine building blocks of our solar system. We've explored its dynamic evolution, constantly sculpted by collisions and gravitational forces, revealing a history far more active than its icy stillness might suggest.
Definitely not static.
And finally, we've looked ahead to the truly audacious future, where this distant frontier could potentially be explored, mined, and even utilized, providing resources, perhaps, to fuel humanity's grandest aspirations for moving beyond Earth.
The Kuiper Belt, this incredible relic of our solar system's turbulent youth, really does hold the potential not only to unlock the deepest secrets of our past, but also maybe to fuel our species' deepest aspirations for interstellar travel. It makes you wonder, what lessons from our past explorations, both the scientific discoveries and the societal impacts, will be most crucial as we look out to these frozen frontiers to try and build the future of humanity?
A profound thought to end on. What aspects of the Kuiper Belt do you find most fascinating? Or what questions does this deep dive spark for you? We'd love to hear from you. Thanks for listening to All in All.